Now that we've looked at the motion of particles relative to each other, so independent motion of particles relative to each other, and we've also looked at breaking up the motion into rectangular coordinates, I'm going to show you a way that you can combine those two problems. So here's an example of relative motion in multiple directions. So we've got a train that's traveling at a constant speed along the train tracks at 60 miles per hour. And we also have an automobile that's traveling along the road at 45 miles per hour. The question is asking us to determine the magnitude and velocity of the train with respect to the automobile. So this right here means that we have a translating plane. So the question is asking, if you're in the automobile, how fast does it look like the train is moving? This is vector analysis because we have particles moving in multiple directions. So for vector analysis, we have relative velocity of the train with respect to A is measured from translating x prime and y prime axes attached to the car A. That means that the velocity of the train in the absolute coordinate system, so the velocity of the train with respect to the origin, if you want to write it that way, is equal to the velocity of the automobile with respect to the origin plus the velocity of the train with respect to the automobile. And the question is asking us to solve for this value. Since the velocity of the train and velocity of the car are known in both magnitude and direction, the unknowns become the x and y components of the velocity of the train with respect to A. So the velocity of the train with respect to the origin is 60 miles per hour in the I direction. So I'm going to define my origin here. So positive direction, upwards positive, to the right is positive. So that's my coordinate system there. So this would be the I direction, this would be the J direction. So the velocity of the train, well, in the absolute reference system is just 60 miles per hour, I. The velocity of the car will be 45, which is the magnitude, times cos 45, because the angle here is 45 degrees. So the x component, which would be along the axis here, would be 45 cos 45 in the I direction, plus 45 sine 45 in the J direction, plus the velocity of the train relative to A. Now all we have to do is rearrange this, and we end up with the velocity of the train with respect to A is equal to 28.2 I minus 31.8 J miles per hour. If we want to know the magnitude of this velocity, I'm going to move this up a little bit. The magnitude of this velocity will be the speed of the train with respect to A is equal to 28.2 squared plus 31.8 squared. The square root of this is equal to 42.5 miles per hour. Now the direction of this speed will be, so we have here we have a positive value in the I direction, and we have, so minus 31.8 J, so that's in the negative direction. So based on the coordinates that I defined, we're looking at 28.2 in the I direction, and we have 31.8 pointing downwards, because remember we had defined our positive direction at like this. So if we have a negative value in the j direction, it means it has to be pointing downwards. So that means the angle, the velocity of the train with respect to the automobile is going to be this vector down here, and we're looking for this angle here. If you want to draw this slightly differently, you could draw this out as 28.2, and you could show the y direction at the tip here, so this would be 31.8, and then you can see that the velocity of the train with respect to A is connecting those two vectors. So the angle here will be tan theta is equal to 31.8 divided by 28.2. Theta is equal to 48.5 degrees down from the horizontal.